I'm going to be going through a taster lesson, give you an idea of what electronics is like at A-level here at QE. First of all, if there's anyone who can't hear me, then if you can let me know, and we can make sure that that problem's solved. So if you can just type a message in, and the support person will be able to read that message. Okay, so what I'm going to do then this morning is to go through a bit about what electronics is, give you some idea of some of the sort of activities we'll be doing, and then I'll go through what the course is about and give you an opportunity to ask questions at the end. Okay, so the first thing is that electronics is everywhere. It is all around you. We use it all the time. From smartphones to smartphones, hopefully that's mine, hopefully it won't go off. Memory sticks, wireless communication, it's all around us. It's around the home. It's used in your doorbells, your washing machine. We spend about 7.5 hours every day on PCs, laptops, tablets, phones. And this is all made possible by the transistor. So my assistant's Sarah's just moving this along. Here we are. So these are what transistors are, and they have been the transistors are what have made all this possible. They were first made in 1947 at Bell Laboratories in the USA, and it's estimated that there's a septrillion of them that have been made to date. That's a 3 followed by 21 zeros. Let me show you what that means. Which way are you going to go? Okay. So that means a 3, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, run out. 21 zeros after the 3. That's how many transistors have been made. It's a huge number. Yeah. It's more transistors than there are people on the planet, then grains of sand on the Earth, then stars in the Milky Way galaxy. There's 2 billion transistors carried around on your smartphone in your pocket. 54 billion on the laptop here that's casting this session. And this is all achieved by making the transistor smaller and smaller. If I just move this up to you, you can see these two are about the size of the original transistor. In fact, the very first one was about the size of a tennis ball, but these are single transistors. Things were improved. By 1970, we got to an integrated circuit like this, which has about 1,000 transistors on. And now, these familiar integrated circuits from inside a computer, one of these has about 46 million transistors on. Okay, so they've got smaller and smaller and smaller. So nowadays, a transistor is about 15 nanometers in diameter. That's a 6,000th of the width of a hair. And really, it's going to be very difficult to make them much smaller than that. Effects like quantum effects become a problem at that level. So what do we do with transistors? What can we do with them? Okay, one of the key uses of transistors is as a switch, and they can make things. on or off. Okay, so if we just put this down, on or off. So if something's on, that's one state. If it's off, that's a different state. So you've got two states. So those states are what we call binary, because there's only two states. So that is high or low. If it's on, it's high. So that's 5 volts. It's a high voltage. If it's low, 0 volts, low voltage. So we call the 5 volts logic 1, and we call the 0 volts logic 0. Okay? Now, what we can do with this is sorry.
No.
What we can do with this is we can count. So we can count in binary. So 0, 0 is the number 0. 0, 1 is the number 1 in decimal. 1, 0 is the number 2. And 1, 1 is the number 3. So you very quickly need extra bits. Each of these is a bit. So just as with tens, with decimal, sorry, we have units and tens. Sorry, this is turning into a maths lesson, but it isn't going to be really. So if I have the number 15, that's 5 lots of units and 1 lot of 10. Okay, so if I'm counting in binary, that will be units and numbers of 2. So the number 1, 1 is 1 unit, and 1, 2, which is 3. So counting up with 2 bits isn't very exciting. So if we have 3 bits, what I want you to do is just have a go, see it on a piece of paper or something. Just see if you can work out what the counting is up to 1, 1, 1. I'm going to give you just a few moments to have a go at that. Okay, let's see how you've done. So I'm just going to fill that in. When we get to 0, 1, 1, we then need to start on the next column, because you can't have a number greater than 1 in each column. Yeah. Get rid of that bottom one there. There we go. So there's 8 possible combinations. And we can use that to make choices, make decisions on which combination gives an output. But we can also just use it for counting. And we've got something here that's actually doing that. So yes, we could just move along, please. Okay, so this is a complex circuit. There's a lot on here, and I'm not going to talk you through and explain it all. What I'd like you to do is just have a look at this side here. Now, can you see these 4 LEDs are counting up? Okay, so we've got all of them are off. Then you've got that one, then that one, and so on. It's going faster than I can talk to you. So this is counting up. This is actually 4 bits counting up. And you can see the decimal number, we've converted it into a decimal number below. So you can see what the binary is and what the decimal is. Now, what's the advantage of a binary number? What's the disadvantage of a binary number? Okay, so a binary number is just noughts and ones. It's on and off. So it can work very well in a computing system, in a switching system. But they're not easy to read, are they? It's very difficult to work out what actual number that one's counting there. Whereas the display is very, very clear. So the big advantage of a decimal number is we can read it easily, whereas a binary number, very difficult to read. Yeah, I think we'll... Oh, no, I wanted to say one other thing about this, sorry. This is a typical sort of project that students make. Okay, so they've made this on a breadboard. It's got lots of different components. We've got switches, resistors that we can adjust to get exactly the right speed for the clock here. This is some logic work here. We've got then a binary counter here and a converter here for the 7-segment display. So making this on a breadboard with the individual components and wiring up and so on, that is all what you'd be doing in a project. And you can choose, when you do this in the second year, you're using all the electronics that you've done before, and you really apply what you've learnt in whatever electronic system you choose you want to design. So that's sort of digital work. What I'm going to do now is just talk to you about some analog work. So the course is kind of two aspects, digital and analog. And that applies not just to control, but also to communication systems. So if I have an amplifier, so that's a symbol for an amplifier. And let's say it's got a gain of 3. So that means it multiplies the input by 3. So if the input is 2 volts, then we multiply that by 3 to get a total gain of 6 volts. And that's the that's the sort of principle of an amplifier. Okay, so if I give you an example of one to do, so we've got an amplifier with a gain of 2, the input 3 volts. What's the output voltage? And the output is, of course, 3 volts times 2, 6 volts. So you can look at this another way, and we can say if the input voltage is 1 volt and the output voltage is 4 volts, what's the gain? So the gain is given by V out over V in. Of course, this is V out, that's V in. So here we've got 4 volts on the output, 1 volt on the input, so the gain is 4. Now that's easy to do if you've got fixed voltages. but these systems are also used for audio signals and waveforms. So if we have V in there and V out there, we might have a waveform that does that, and the output will be an enlarged version, like that. So that will be V in, and this larger voltage here will be V out. Okay, so we're going to look at a system that uses that. So if we just move along to the setup I have here. A little bit more that way. Yeah, that's it. Good, thank you. So what we have here is the circuit. This is the amplifier. It's got a few resistors and so on around it as well. We've got a signal generator on the left. That's giving the input voltage. And we've got an oscilloscope on the right here that's giving the output, and it gives us a display. So perhaps we could have a look at the display, please. Oh yeah, would you mind just doing the light? So obviously you'll be doing experiments and circuits like this yourself in a real lesson. And if you'd been able to come into college, you'd have been doing this yourself. So we're showing you the sort of things you would be doing, but obviously you'll be doing this yourself. So the red waveform that you can see there, that's the input voltage. Okay. The yellow one is the output. So they're both on the same scale, 5 volts per square. So can you see what differences are there? I want you to have a look, see if you can identify 2 differences. Have a look carefully at the waveforms, 2 differences. Okay, so the first one is that the yellow waveform, the output, is much larger than the input, the red one. So we've got an amplification, we've got a gain, and we can measure that. We can measure that by measuring the height, the amplitude of the 2 waves. Now, I said a moment ago, each big square is worth 5 volts. That's the setting I've got it on. So the input is only 1/5 of a square. So the input is just 1 volt. The output is 2 big squares. So that's 10 volts. So what we've got is a gain of 10, haven't we? The output is 10 times larger than the input. But what else do you notice? If you're really observant, you'll notice that when the red one goes down, the yellow one goes up. And when the red one goes up here, the yellow one goes down. And you'll see it a bit better if I change the scale so they're on a different scale. Now I'm wishing I hadn't done that. Just getting the trigger waveform to stay still. There we are. And you can see very clearly that the red wave goes down, the yellow one goes up, the red goes up, the input goes up, the yellow one goes down. So that's what we call an inverting amplifier. Okay, and I'm just going to change the scale on the yellow one again. And what I'm going to do is increase the size of the input voltage. What do you notice about the yellow waveform? What do you notice about the output there? As I increase the size of the red wave, the input, what happens to the output? So you should notice that it loses the curve at the top. And that's called clipping. And it's a form of distortion. And if that happens, it really is a problem in the electronic system. Okay? So that gives you an idea of some of the analog work we do. Yes, please. There's one other piece of apparatus I want to show you, and then I'll give you a summary about what we're doing, what you'll be doing, and give you a chance to ask any questions. So what we've got here is it's another piece of kit that we use to program a microcontroller. Yes, please. We'll just put some lights on so you can see better. So the microcontroller is just this integrated circuit here. Let me lift that up. You might be able to see it a bit better. It's this integrated circuit here. Just that little one there. So the rest of this is for putting the program on it. You actually use a program language called MTASM on the laptop here. You program it in the laptop. You download it onto the microcontroller, and then you can test it with the devices on the right here, or you can take the microcontroller off the board and put it in your breadboards like the circuit that we saw earlier. And that way you do some project work with this programming device, this control device. Okay, so I'm just going to show you a PowerPoint presentation, and then I'll give you a chance for questions. So, sorry, there we are. So, yeah, what I want to do is give you an opportunity to ask questions. So, if anyone's got any questions about this course, it's obviously a full A-level course. It's examined by 2 written exams in the summer, and 20% of it is coursework, making projects of the sort that you've seen with microcontrollers and with circuit board. The course is run by Educast, which is the English arm of the Welsh exam board, and we've got years and years and years of experience of working with them. We're a highly resourced electronics lab. In fact, if no one's got any questions, I'll give you a quick zoom round of the camera. But there is a question, so I'll just answer that. Raphael, hi Raphael. During this work, would you use multiple computer languages? No. The only sort of computer programming side of it is with this microcontroller, and that's one piece of work, about 4 or 5 weeks, where you learn the program and then you do a project on that yourself. You could use the microcontroller in the main project. Some students do, some students don't. Okay. I hope that answers your question. Most of the time, what you'll be doing is making circuits, testing circuits, analyzing them. You'll be applying the theory that you learn for circuit analysis. There's an element of mathematics, but there isn't the requirement of mathematics that there is for a course like, say, physics or computer science. Okay. What electronics goes really well with, though, is those sort of subjects, the physics, the computer science, IT. It goes really well with IT or design, because you're using the same idea of the design that you're using in an art and design. That sort of coming up with a brief and a specification, looking at different ways of making your system, and then making it and testing it and analysing it. So you'd be using a lot of test equipment, things like oscilloscopes, as well as multimeters, logic probes, the whole range of test equipment, and we've got vast amounts of it, so you can work with that individually on your own. Can't see any other questions at the moment. So just waiting to see if anyone's got any further questions. While you have, I can give you a quick tour round. Sorry, that was it. So I have no idea what you're seeing here, so let me just so this is the lab. You've got sort of equipment components there. As we come around here, we've got thank you. We've got sort of oscilloscopes, signal generators, power supplies, all sorts of equipment there. At the end there, you can see the coloured trays. Each student has their own tray to work with, with all your components, test equipment, everything like that in it. We do, if you look at the whiteboard there, the electronic whiteboard, we've got, we use software to, sorry, I'm thinking about where I'm putting the camera. We use software to model circuits and analyze them as well. So we do that virtually. So has anyone else got any questions? We've just got a couple more minutes. What I'll do is I'll make sure the PowerPoint is available for you so you can have a look at it. If you've got any questions, then do contact the admissions team at the college. They'll be able to put that message through to me, and I'll be able to answer any questions. Or you can email me directly at david.loma@wqe.ac.uk. Okay. I do hope that that's been of some interest to you, that you've seen something you like and you can see how exciting electronics is. It really is what engineering is all about. It's what sort of a major part of the UK industry is about as well. We've got a huge electronic engineering industry in this country, so really good employment possibilities. We've got just time to answer this question. This is from Trishul. I'll put my glasses on for this. For a final assessment, do we need to create something, or will it be all paper-based? No, you absolutely need to make something. And that would be on a breadboard. Sarah, would you mind just unplugging that breadboard and bringing it over? So that would be on breadboard. So like this. And you'll be building a circuit like this. You'll be designing it and building it, and it will be doing something that you've chosen, that you want to make. It's really exciting part of the course. We spent about 8 weeks doing that in lessons, outside of lessons. It's really good fun. So I'm going to have to finish here, or I'll get told off for overrunning. But as I say, contact me at college here if you want to find out anything else. You can carry on typing in questions, and I'll be able to answer those as well. Okay? I hope to meet you all in September.